Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. First off, I'd like to thank Stanley Consultants for sponsoring this webinar. Here with us today, we have Paul Chanowski, founder and president of Resilient Analytics, which is a Stanley Consultants company. We also have Jacob Hellman, lead engineer at Resilient Analytics. Serving as our moderator is Professor David Zombach from Carnegie Mellon University. Professor Zombach is a board-certified environmental engineer and has been with the Academy for 27 years. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. Before we get started, Professor Zombach would like to say a few words. Good morning. How are you?
Hi, thanks, Marissa, and thank you all for joining us today. I'm really looking forward to today's webinar on what I refer to as a grand challenge for civil and environmental engineering, for all of engineering, the climate change, the changing climate, and how it will affect the work of all of us. We're very grateful to Stanley Consultants for supporting today's webinar. Stanley Consultants, over 100 years old, founded in 1913, has been working on a wide range of problems, helping clients solve essential energy and infrastructure challenges, and they continue that work today with service in all over the United States and internationally. I encourage all of you, especially the students, to take a look at the website for Stanley Consultants, www.stanleyconsultants.com. And they have international offices. They're working all around the country and the world, and there are good career opportunities there for any of you. It's a pleasure to welcome today Dr. Paul Chanowski, as Marissa said, founder and president of Resilient Analytics, a Stanley Consultants company, and Jacob Hellman, a lead engineer with Resilient Analytics. A little bit about Paul and Jake. Paul, as I said, is a founder and president of the Resilient Analytics and the director of the program in environmental design at the University of Colorado, Boulder. In his consulting work, he is very much focused on the changing climate adaptation. His approach is to incorporate an evolutionary approach to climate adaptation to increase resiliency on projects for clients. Paul holds a PhD in civil engineering from Stanford University. Jake is lead engineer with Resilient Analytics, specializes in energy demand modeling in buildings, as well as analysis of climate impact data. Jake has led several major initiatives for the company, including development of water utility, coastal protection, rail, and building impact modules. Jake joined the company after receiving his master's degree in architectural engineering from the University of Colorado, Boulder, and his bachelor's degree from the University of Pittsburgh, right across the street from where I am sitting today. Both Jake and Paul are located in Boulder, and without further ado, I turn the floor over to them for today's presentation on the new era of climate change, turning risk into opportunity. Thanks, Paul and Jake. Look forward to your talk.
All right. Thank you. Good afternoon, everyone. There we go. So today we're going to be talking about climate change. And climate change is one of those interesting topics that probably everyone you talk to has a different concept, opinion on what it means, and what we should do about it. Should we do anything? Should we wait? And that really makes the topic an opportunity. It's not just a risk. When we talk about it from an engineering standpoint, there really is a fundamental change to our entire profession going forward. And today's talk is really about what are the opportunities, what's happening, some specific examples that we've worked on to help illustrate what it is that there is a potential to do and how are we going to be impacted. Jake and I are going to be collaborating on this presentation, so we'll be going back and forth a little bit on this as we talk about different pieces. But I'm going to start with giving a little introduction to who we are, you're probably wondering why are these guys giving the webinar, and talk about that a little bit, and a little bit of an intro to climate change itself. So, and the other key piece right near the end is this really engineering opportunities and where to start. We want everyone to leave today with an understanding of, hey, if I want to get involved with doing something about climate change, helping people out in the environmental context, where do we start? And we want to give you a little bit of a taste of, here's where to first look. So just a minute on who is Resilient Analytics. We've been doing infrastructure work since way back in 2006 when we started with roads in Alaska. We've been really focused on the central question of what is the cost of climate change to infrastructure. We work primarily with cities and counties and states, the EPA, but also we've been doing a lot of work internationally. We've worked in over 50 countries doing this, everything from developing areas in Africa and Southeast Asia to working in China and Korea, pretty much all over the world. Right now, we're pretty excited. We actually have a project on all 7 continents at one time right now, and that's pretty exciting. Last year, we became part of Stanley Consultants, really to increase the depth of engineering, and they wanted to really bring actively climate into their considerations. So let's start for a moment at a broad context of climate. And anyone who looked at the TV this morning was seeing severe tornado impacts along the Gulf Coast. Some, to an extent, I was really struck. Normal average tornadoes in the month of January across the country is 36. We've had over 150 this month already. Why? Because of changing weather patterns. We're seeing warmer water, we're seeing changes in the jet stream. And what this graphic, I think, so perfectly encapsulates that just in 2022, these were the billion-dollar weather and climate disasters. And you see it's everything from hurricanes and tornadoes in the south, hailstorms in Texas, wildfires in the west, drought. And we've had a lot of rain in the west, alleviating drought a little bit. But of course, now we have floods. So every part of the country is experiencing change. And some people say, well, is this just an anomaly? Is this a one-time type of event? And we look at the trend, we go back over the last 40 years. This is not a one-time anomaly. We see increases in all types of events, flooding, winter storms, and you see especially in severe storms. That's one of the things that we are going to see continuing. We are really in the age of a change in the type of events. Now, this is serious enough on its own. When we combine that with our aging infrastructure, we essentially have this double impact. If we go back to the 70s, we were in this golden age of infrastructure building. Well, most of this infrastructure was only expected to last 40 or 50 years before it was redone. Well, here we are 40 or 50 years later, and we are facing not only aging infrastructure, but we're facing a changing environmental condition that we're working in. And that is the double impact. We're seeing this trend continue, and we've got to figure out how to deal with resilience. So Jake, I'll let you pick up on this one.
Thanks, Paul. And adding to that, it's not only about the increase in frequency and the age, but there's also a increase in exposure because we are putting infrastructure in places that hasn't currently been there. So all of these things are compounding and they're impacting all sectors and all disciplines of engineering. As you can see on the slide, we just have a few examples on just how this is impacting environmental engineering, and from water supply to water treatment, drought and reduced runoff can lead to a decrease in water supply. An increase in water temperature can reduce drinking water quality. Wildfire can also impact water quality, near term and long term. Extreme precipitation events can compromise drinking water sources. On the wastewater side, extreme precipitation events can cause higher inflow and infiltration, more frequent bypassing, and sea level rise has a big impact on potential outfalls. Air pollution, there's a number of different ways that air pollution is impacted, between higher temperatures and ozone concentration, wildfire that can produce harmful particulate matter. And on the other side, there's land resources and erosion. Drought can have a really big impact on food production and the need for irrigation. It will shift land use practices. Soil erosion can be exacerbated, and ultimately sea level rise can change soil in coastal areas and bring in contaminants. And this is only a short list, and this is only for environmental engineering. This is really why this is such a grand challenge, as David mentioned. And it's something that needs to be considered. And it's something that clients and developers and investors are starting to notice. And it's something that all engineers are going to have to start to integrate into their design. Next slide, Paul. The market drivers and opportunity, and this is where the opportunity starts. So climate change is not an abstract concept anymore. It's a concern that is appearing in RFPs and developer discussions and investment decisions. I think as more and more people are impacted by changing climate and extreme weather events, they start to realize that this is something that has to be considered, and it's something that needs to be considered on a number of levels, financial and social and many others. And once again, this falls on us as engineers to be prepared for this. And ultimately, the goal is to avoid climate risks and for it to be incorporated as a new standard. And there's an opportunity to get ahead of the market and to start designing with trusted partners and with owners and understanding climate risks, and also with partners who are ready to implement a new risk metrics. There's a lot of uncertainty within climate change and infrastructure, and there are a lot of design challenges that need to be navigated. So we'll take a step back here and just think about climate in engineering design. And I think a lot of you are going to be familiar with some of these design considerations, which for wastewater treatment inflow, we're thinking about recurrence intervals and the IDF curves, the 5 and 25-year, 60-minute precipitation. Everybody is probably familiar with the NOAA Atlas 14 precipitation frequency estimates. And those are looking backwards. Those are looking back in the last 50 or 80 years. But if we're looking forwards, and we are projecting a 5 to 30% increase in intensity in a certain area, how does that impact design? And for a drainage calculation, if we're using any method, rational method or the like, if we have a 10-acre site with a runoff coefficient of 0.26, the 10-year, 20-minute storm is 4.8 inches per hour. We have a peak flow of 12.5 cubic feet per second. But for the same infrastructure that is going to have a lifespan of 20 or 30 years, if that increases by 20%, the intensity to 5.76 inches per hour, that peak flow is now 15 cubic feet per second, which is a substantial increase and ultimately could be the difference in whatever you're trying to size, whatever design element it might be, whether it's a swale or intake or culvert and things like that. For a retention pond, there are other considerations. It's not only looking at precipitation, whether it's the maximum wet year, but it's also thinking about evapotranspiration. and how these impacts could be compounding or offsetting. And ultimately, it leads to the main question, which why are we designing the infrastructure of the future to past climate conditions? And historically, that's the only data that we had to go off of. But now climate modeling and climate science has changed that narrative. And it now gives us an additional tool for design. And it gives us the capacity to design infrastructure for the future. Having said that, there are a few other things that need to be considered. There is uncertainty in it. Climate modeling and climate variables need to be, from temperature to precip, they need to be transformed, or there needs to be a calculation to get to the variables that we need. And sometimes there are limitations to what you should and can be looking at. And that's just the beginning of it. And climate projections is where it starts. So with that, I'll turn it back to Paul, who's going to do a deeper dive into climate projections, and then we'll start looking into some case studies.
All right, great. So I always like to start with addressing head-on questions about how uncertain are we about climate change. I think that's a really important thing. And the one piece that I always tell my students and everyone that we're working with is if somebody comes to you and gives you one number and says, we are going to see a 3-degree maximum temperature impact in 20 years, or we're going to see an increase of precipitation of this amount, that's the answer. I always say, turn and run the other way, because there is not one answer. There are many models of climate change and multiple emission scenarios, and that's okay. Every major research group around the world is developing climate change projection models. And I say projection and not prediction. Models are deterministic. They are as close as we can get to trying to figure out what will actually happen. It's not probabilistic. There aren't probabilities on climate change. Why? Because we've never experienced this before. We don't know. There are levels of agreement. So we can say that over half the models are projecting this might happen. But that's where we have to focus. So you can see in this little graphic here, there's roughly about 30 different models out there. Each one of those models run across different scenarios, emission scenarios. Everything from the world's going to get together and we're going to make a very strong set of agreements limiting emissions and growth, to nobody's going to have an agreement on anything and things are just going to continue to spiral. These are what you'll often see as what are called RCPs. They're really concentration, they're emission scenarios, they're economic scenarios. And you can see they go out all the way to 2100. Well, if you look at this graphic on the right, this is just part of all the different systems that are in climate models. And some people focus more on ocean evapotranspiration. Some people focus more on runoff. Some people focus on atmospheric changes. Each model is going to be slightly different, which is why, well, if you're getting into this, you have to commit to understanding that there's variance. You have to be comfortable with that variance, comfortable with uncertainty, and understand the limitations of what you're looking at. And you have to look over the complete type of data that's available. Now, this brings us to our first question that as environmental engineers we have to face. There are many clients that will say to you, I want the answer. Tell me what the answer is that I should design to. And you can't. There is not one answer. And you should never be telling somebody there is one answer. You have to tell them there is a range. Now, depending on what they want to see, they might say, well, I want to see midpoint to most severe or midpoint lower. That's their decision. But we have a responsibility to let clients know that there are multiple models and answers. It's our job to work within that as uncertainty. Now, part of that uncertainty comes with what's called downscaling. You'll hear this resolution, downscaling, granularity. These are all terms that are kicked around all the time in the climate world. And if they are important, they're very important. So we see at this top graphic, and this is typically the way most raw climate data is generated, typically on about a 50 or 100 mile square area. Some of them are even 200 miles square. That means that there is a lot of topography and situations that are averaged out. To overcome that, we downscale. We try and match the climate projections with historic data and either model at a smaller level. You'll hear people talk about regional climate models, or statistically look at how we can match to try and bring back, as in the lower graphic, more detail in the topography and thus more detail in the actual projections. Now, there's a question for this. And as an engineer, this is something you have to be very, very careful about. So this last bullet, unrealistic accuracy. How good a resolution can we trust, and how do we use it 20, 30, 40 years in the future? Can we say that within this 5 mile square, the temperature in the summer, 20 years from now, is going to be 2 or 3 degrees maximum higher? That's one way of describing it. Some people want to describe within this 100-meter area, 20 years on July 15th, it's going to have a maximum temperature of 93 degrees. Is that accurate? Is it unrealistic? I've seen people now coming out with half kilometer. In this half kilometer area, 20 years from now, we can expect there's going to be a ½ inch of rain. Is that unrealistic? We have to make, everybody has to make that decision. What is the client happy with looking at? If you're going to try and get very accurate, you need to put a lot of caveats behind that. This is where uncertainty comes in. Is there an appropriate way to use this as an engineer? Jake's going to talk a little bit about that in the case studies, but this is something that anybody who's going to get into climate resiliency needs to address. What do you feel comfortable using? What level of accuracy and granularity do you feel comfortable with? And what do you feel is appropriate to tell your client? Those issues become very important as we're making detailed engineering decisions. Unfortunately, I can't sit here and tell you what is right, what is wrong. All I can tell you right now is there's not one answer. Don't use one answer. You've got to look at a range of data. You also have to look at the challenges of what are the variables that are available to you. So climate models have these base variables: humidity, precipitation, wind, temperature, solar irradiance, valuable information. But to get to engineering, you actually have to do some derivation and transformation. If you want to get to wildfire threat, drought, cooling degree days, heating degree days, flood events, these have to be derived. So there's an engineering challenge here. What do you want to take on yourselves? What do you want to partner with? What is important for actually developing design criteria? So for example, looking at augmenting here extreme heat days. What often question when you get to water quality, when you're getting to drought, how many are above these extreme heat days? Well, you have to take a look at that. You have to calculate it. This is where decisions come into play about opportunity. Where do you want to play in this? Do you want to be a data consumer from someone else and just enhance your engineering designs? Do you want to get into the data generation game and start looking at this? There's plenty of room for all different types of players. But understand that when people talk about climate change variables, they're just talking about these base variables. They're not talking about them in ready to go for engineering design. You have to go further than that. So the last piece I want to talk about for just a minute is what level are we talking about? We always talk about 4 levels of climate fit into engineering, the role it plays. Level 1, which you see all over the place right now, awareness. What are the future conditions? This is the race to make the fanciest maps that have the most information that look the best. Lots of people from the federal government to GIS companies to nonprofits, everyone's making maps now just of what is the potential climate change. Interesting, important, not enough to do engineering with, but it is where most people are at, just getting aware. The next level, vulnerability, some of this is available. A lot of this is what you as engineers have to start looking at. What specific assets are going to be vulnerable to climate change impacts? Not everything's going to be even. Not everything's going to be negative. One of the hardest messages to get across is there's actually some places that are going to benefit from climate change. And I can't tell you how many times we'll do a project for a client and we'll come up with saying, yeah, there's not really any change in this specific location, or things might get better. And they'll come back to us and say, are you sure? Shouldn't it be worse? I'll say, well, in general, yes, but in this specific location, it may not be. And people have to be comfortable with that. But where we really get into engineering is getting into these levels 3 and 4. And I have a line here really because the vast majority of clients and information out there are not at this level right now. And this is what a role as an opportunity for engineers is coming in. Figuring out what is the financial cost, the operational costs that's going to happen to a specific asset. Strategic, what should you do about it? What are the adaptation options? How do you prioritize? This is really where you're getting into the value add. And this is where people need to start thinking. It's not good enough to just map an impact. We have to talk about where it's going to be. So I want you to keep those things in the back of your mind as we go through this remaining part. There's uncertainty in climate models. There are many climate models. There's different scenarios. There's issues with downscaling and resolution. And we have to get past just being aware to actually answering the question of what we're going to do. I want you to keep those things in the back of your mind, not because it's saying we can't answer anything about climate change. It's saying go into it with your eyes open. What are the factors that need to be considered? So I'm going to pass it back over to Jake, and he's going to start getting into some real application examples. So Jake, it's all yours.
Thanks. So before we get into a case study, we'll just touch on the application of climate projections within engineering. And there are many different types of risk that we've categorized. And the first would be design risk. And design risk is thinking about design standards. It's thinking about how we are building infrastructure based off past climate data. And ultimately that is going to be in future conditions that we now, from climate science, have an indication of what that might be. So that's design risk. Acute risk is risk for extreme events. That could be flooding or wildfire or anything like this. And ultimately it is assets that would be in an area, whether it's a floodplain to see increased flooding or wildfire prone areas, and would cause some sort of failure because of a catastrophic event. And there's also operational risk, which is more of a chronic risk. So that would be increases in cooling over the next 20 years and how those operational costs might be, or road maintenance costs, increases in maintenance for pipelines, things like that. And then finally, after you've evaluated all of these risk criteria, it's about adaptation. And this is ultimately where the opportunity comes in. And adaptation should be looked through for a number of different lenses, financial, there are social lenses, and even from a policy standpoint as well. And we'll kind of go through some of these risks and adaptation in a case study that we did for some water utility groups. So the objective of this case study, which we did in collaboration with the Water Utility Climate Alliance and the Association of Metropolitan Water Associations, the goal is to understand the impacts of extreme heat on public water utilities, and ultimately how those impacts will be different in different sorts of climates. And I think when you think of water utilities, you think of changes in precipitation and how those will impact. And that is certainly going to be the case. There will be changes to water supply and some of those things that we talked about. And this was a unique study because a lot of people wouldn't think about changes in extreme heat events as being so critical to water utility infrastructure. But it is for a number of reasons, and we'll get into some of those critical assets. And another huge thing is talking about personnel. There's a public health aspect of this, and that can't be overlooked, because when it comes down to it, outdoor workers and anybody working in some of these conditions, those considerations need to be taken ultimately, so that companies, clients, and all of these have the proper safety protocols. So next slide. For this analysis, we split it up into a few areas of impact. First was personnel, thinking about health and safety, and productivity on warmer days. Ultimately, work rest cycles tend to increase and maybe less can get done in the field. Second was electrical equipment. So this would be degradation of lifespan, specifically within motors and motor control centers. And there is a rule that we'll get into on the next few slides, which discuss lifespan and heat, and how heat has a negative impact on lifespan for these motors. And for some of the critical facilities, such as the pump stations, this could have a huge impact on replacement of these motors and some of those failures. The third is cooling costs, how cooling equipment might have more energy demand just based off of the increase in usage and temperatures. This would be an operational risk. And then finally, other facilities, which these water utilities are also tasked to maintain. So that would be roofing and parking lot. And as we discussed this, a lot of these, at first glance, you wouldn't think would have such a huge impact. But the reality is climate change impacts all operational areas for a client or for a utility and for any other asset owner. So first, we'll get into personnel. So projected heat index was the metric that we used. And before we get into some of these details, it's also important to note that for this, we were using only temperature, Tmin and Tmax. And the first thing that we did is we evaluated how well the climate data and the climate data sets were representing the current conditions. And this is incredibly important. For this, it was looking at heat index and daily maximum temperatures and average temperatures and cooling degree days. And before you can carry out an analysis, you need to see, is the climate data and are the climate variables that we're thinking about represented well by this climate data set, and comparing and evaluating a few different databases. And ultimately what we went with is an industry standard, which is called the Localized Constructed Analogs data set, which is for the US. It's at a 16th degree, and it has a number of models and scenarios. And by comparing the baseline of this model data to observed data in each of these 5 locations for these 5 water utilities, we determined that it did accurately represent the variables we wanted to look at. And as you can see, you can talk about the increases in days over certain temperatures and the wide variety across these 5 different, geographic locations. So Portland, which is pretty cool, does see some increases in days over 90, 95, and 100, but it doesn't span much beyond that. For Southern Nevada, we see huge changes, and changes that go all the way up to 120. Miami-Dade is interesting because the summertime temperatures tend to be in the 80s and just below the 80s, and there's this huge switch to the 90s, and they're going to have impacts on the workers. And ultimately, this study came and fed off of a few public health studies, some from MIT and others, and some of the high-level conclusions are that there will have to be more rest work cycles. And in order to accommodate that, there's going to be a loss in productivity. And that bottom right corner, you can see annual changes in lost productivity. And you can see the huge range, right? We're talking about multiple scenarios. So RCP 4.5 would be a lower warming scenario. And we see the different timeframes: 2030, 2050, and 2070. And moderate and standard and strict would be different types of work rest cycles. And this is what Paul was alluding to, that there are pretty large ranges, and we have to navigate that, anywhere from 15,000 in 2030 to 66,000. And then once we get to 2070, we see even bigger changes, anywhere from 43,000 to 310,000. And how do we evaluate that? And we did that through talking with the water utilities and providing all of this information for them to make decisions internally. And for personnel, it's really important because projected changes in workplace accidents, if adaptation didn't take place, there was an increase in 8% to 17% in some locations, which is a pretty massive increase. So trying to offset this and then thinking about adaptation was this next step, which we'll circle back to. Next slide. Next is electrical equipment. And this is the critical infrastructure we were discussing. And ultimately, electrical equipment, motors, motor control centers, VFDs, all operate within some ambient temperature condition. And as the ambient temperature increases, the expected lifespan decreases, and vice versa. And this is what we modeled. We worked with the water utilities, and we got monitored climate data in a variety of different assets to see the temperatures that these critical assets were exposed to, created relationships, and then projected those forward. As you can see in the figure to the right, facility 4 already had a huge issue, which seems interesting and almost seems like it would be incorrect, but this was an underground facility that had such a high internal load that even from the baseline perspective, they already had problems with cooling and cooling center. And these were all unconditioned spaces in this case. There were also some spaces with were conditioned, and then those conditioned design standards weren't met because they were sized for only certain temperatures. And ultimately, as we start to creep above that, we start to get creep in the internal temperature, and then we get decreases in the lifespan. Next slide. These are the curves for the activation energy and ultimately the acceleration factor. So this is for every 10 degrees C increase, there is an acceleration factor depending on the activation energy, on average about 2. That means the lifespan decreases by 1/2 if the motor is operating in 10 degrees higher. So that's a pretty massive change. And when we're thinking about changes in climate, and we're thinking about a few degrees by 2070, the lifespans get reduced by a number of years, which costs money. Next slide. And this is a table of one of the water utilities and how some of these costs and changes or upgrades and having to switch out these motors would cost. And for each facility, they range widely based off the internal conditions and by all of the scenarios and how often they run, whether it's 12 or 24 hours. This once again goes to the uncertainty. For facility one, we're talking about 100,000 to 684,000. That is a massive difference, and deciding on which adaptation and thinking about return on investment is an important part of this. An important part of feeding that information is understanding all of the possible scenarios. Next slide. For cooling demand in facilities, there were a handful of the water utilities that have conditioned internal spaces, and the cooling costs are projected to increase by 4 to 5% by 2030 and 9 to 13% by 2050, and by 2070, 12 to 23%. And these are pretty huge. If you think about how big some of these demands are, we're talking in the millions of dollars over that time frame. And the adaptation can be justified because of some of these increases. So now if we're installing a high efficiency chiller, from the baseline, the return on investment might be, if you look at the third facility down, 30 years. And now by 2070, it's 21.8 years. So now maybe you have justification to start increasing that efficiency. And this is when we start thinking about risk and regret in adaptation decision and investment, which is that level 4. And along with the cooling demand, we also looked at some of the roofing system and parking lot surfaces and their shorter lifespans, and ultimately recommending these additional costs need to be considered in near and long-term budget planning and working with the water utilities through that. And finally, there's adaptation, which was the main objective. It's how can these water utilities think about extreme heat in their operation and ultimately make adaptation solutions that work for them. For personnel, the interesting part of this analysis was the geographic differences. Portland, which is really cool, had very little heat training in place compared to Miami or Southern Nevada. So there was a lot of collaborations amongst the water utilities in coming up with these adaptation options and worker scheduling, flexing them to the morning to avoid the hottest parts of the day, adopting a new rest cycle standard, and even thinking about confined spaces. There are also some unique challenges with water utilities where they had to do confined space work and flexing that confined space work to a cooler day or the morning or even the evening sometimes. For electrical equipment, there were adaptation recommendations for higher insulation temperature ratings and enhancing maintenance schedules and having replacements on hand in case some of these lifespans get shorter so that you don't have to wait and the critical infrastructure isn't down for so long. For cooling, we recommend commissioning and envelope improvements, airside economizers, as we talked about before, increasing the efficiency of chillers and thinking about that return on investment. And for facilities, there are some pretty simple changes to design, whether it's cool roof coating or upgrading in binder and design temperature. So the whole goal of this project was to think about the water utilities and think about the impact of extreme heat. And we going through these stages of evaluating climate data. What are the acute risks? What are the operational risks? What are the design risks? What are the costs of these risks? And then looking to adaptation and how these adaptations can offset some of these costs or personnel safety hazards, and ultimately coming up with a strategy for each of these water utilities looking to the future.
All right, so I'm going to now, in this last part, give you some examples. Jake went really in depth with getting into what level is actually looked at, and I'm going to talk about how this affects all different regions in ways that we may not think of. So here was one Boulder, And it's kind of funny, everyone says, oh, you guys are in Boulder. Obviously, you did this. We actually spent a good decade saying we're not going to do Boulder because nobody would take it seriously because we were here. So they finally talked us into looking at our own town. And what you see here is wildfire increase. Again, big issues with water quality, drought, water supply. As now everyone's talking about water supply in the West, what are we going to do about that? Cooling centers, system capacity for urban drainage. Again, that goes to so many of our urban drainage areas. Our stormwater systems are not going to be able to handle the increased intensity of storms. So what do? Even things like impact to roads and bridges all come under this same focus. One of the things that people don't often think about is water intensive operations, data centers. So data centers are a huge user of power, but they also use a lot of water for cooling, and especially for emergency cooling. There's actually one client we had there, they were talking to us about some of their locations where it gets so bad, the cooling systems can't handle it, and they literally will take a hose and spray down some of their equipment to prevent it from overheating. So there is a huge high-tech interest in water supply. What's going to happen? Can be guaranteed to make sure operations work. Sea level rise, coastal. There is an immense amount, as most of you know, of infrastructure that is along the coast. Wastewater treatment plants, drinking water plants, stormwater systems, all along the major population areas. Well, sea level rise is probably the most talked about. Also, probably one of the most controversial, thanks to Hollywood pictures, right? We are not likely to have a 10-foot sea level rise overnight, like you see in some movies. It's great for a movie. It's not very realistic. But from an engineering standpoint, there comes to a point where it doesn't matter if it's 1 foot or it's 3 feet. What I mean by that is the impact on your systems start much earlier than the maximum sea level rise potential in storm surge. So for those of you who do work on the coast, it's time to really look at the vulnerability and the likelihood of the alignment of the models of, do we have systems that are going to be underwater in the next 20 years? If you're thinking about drainage systems, there is a very, very significant impact to roadways because of insufficient drainage. We need to start thinking about green infrastructure systems along many of the highways that exist, rural roads, city roads, highways. We have to be thinking of completely new approaches to detention systems, retention systems, drainage. How are we going to start thinking of even simple things like rain pools to slow down that water? How are we going to reduce the runoff of chemicals that are going into our water systems? These are prime concerns of national EPA and local health protection agencies. Tampa, Florida is one of my favorite, I put that in quotes, examples, because the question there is a perfect example of, well, what do we do about it? We can't just be aware of things. We have to think about what we can do about it. We did a study a few years ago about the vulnerabilities and adaptations. And this last winter, the hurricane that was coming up the Gulf Coast actually modeled the exact conditions that we looked at. And there was a large concern because the adaptations weren't all yet put in place. So it is never too early to start thinking about adaptations. Vulnerability is important, but if you can't answer the question with what should we do about it, it's only half the answer. And the costs. Costs are always going to be important. It's always return on investment. How do you offset to a community a savings that may occur 20 years from now with their need to put in place infrastructure right now for a different need? And so there really has to be a focus on return on investment. So where do you start? There's a big problem out there. This is a big issue. And here's 4 basic things that I always tell everyone. Understand the appropriate use of climate models. It's not necessarily appropriate to say on July 15th in 2042, at this specific location, you're going to increase a 1/4 inch of rain. That may not be appropriate, not yet. It may be appropriate to say within this very small area, we project in this month, this trend. Understand the appropriate use. Find the vulnerabilities of concern for the clients. They may not even know what the appropriate vulnerability is. There's a lot of work, as Jake was talking about, our working with the water utilities. You've got to talk to clients and find out what their concerns are. What is the potential for operational impacts? It's not good enough to just say, hey, you have a plant or a drainage system or a stormwater system that's going to be impacted. What is the operational impact? What is potential downfall to it? And where is your benefit? If you're going to get into this, it takes an investment in knowledge. Where strategically is this in your business model? So to conclude, before we do some questions, I hope people have their questions. We've gone over a lot of things. Climate has always been an input to design. But now we've got to think about future projections, which brings up my favorite issue that I always put out there, the ethics question. Legally, we're typically, in most jurisdictions, look at what the standards are, which are based on historic. Ethically, and also from potentially a liability perspective, is it okay to use historic if we know that going into the future it's liable to be different? That's an answer that nobody's wants to go out quite on that limb yet, but it's coming very, very soon. What is your responsibility? And that's where we get to climate considerations require more than just awareness. What does it mean? What's the potential impact? And finally, every location in the United States has some future climate impact, whether it's increasing storms, floods, drought. Every location has a changing condition. Even though we may only hear about the Gulf Coast, we may hear about California, we hear about the Southeast. Every location has an impact. Every location has an impact that changes design. And that's the first point in starting. And I'll stop there, and Jake and I are happy to take some questions.
Thank you, Paul and Jake. That was just terrific. And we do have a number of questions. I'll attempt to group some of these. The first one, there are a couple questions here related to where can I learn more? There's some question about terminology, unfamiliar terminology. What would you recommend as some starter resources where folks could go, engineers, environmental engineers, where they could go to start learning more about climate model projections and some of the topics you've been discussing today, Paul and Jake?
Sure. So the first place I always recommend people start with is the National Climate Assessment. So the National Climate Assessment is put out in the US every 5 years. And it comes in 2 volumes. Volume 1 is more of the science one, where you'll get a lot of information about climate models, about what they mean, changes. Volume 2 is really impacts. And that's where you can really focus on things that are specific to a region, specific to your particular area, whether it's transportation, whether it's water systems. That is always the place to start, in my opinion. Jake, I don't know if you have one to add that you'd also put in.
Yeah, I think there's also the IPCC 6th assessment report, which is really the basis for climate modeling. I think that has some valuable resources. And then within the continental US, there's also CIRA, which would be the climate change impact and risk analysis, which touches on a number of different infrastructure and impacts, and even beyond infrastructure. Really. That's
EPA had put that out.
Right.
And all of these things are free. You can go online and look them up. So it does take some reading, but that's a great place to start before you dive into really detailed things. Get a good broad overview, and then you can go from there.
Thank you. Those are very helpful and important resources. One I would add, another free resource, the American Society of Civil Engineers has a committee on adaptation to a changing climate. And there is at least one free report that can be downloaded with the title, something close to Adaptation to a Changing Climate. So I would encourage folks to look at that also. There was a question here about cost. So you talked, Jake, in the examples you provided, you looked at effects of heat on cost for personnel, break times, and then impacts on electrical equipment. Question is, are there good references for infrastructure cost escalation versus time? That's I guess the question here refers to taking a larger system look, and maybe someone's done this regionally, looking at impacts of, say, extreme heat on a set of counties in Texas, and what's the overall cost impact. Are you aware of any studies like that have looked at particular infrastructure assets and impacts and related costs on them?
Yeah, Jake brought up the EPA CIRA work. That's a great place to start on that. They looked at transport, so roads, bridges. They looked at cold weather and coastal. Some public health work, but it's a good place to start that actually has cost numbers in it. There's quite a bit of research out there that you can see in the last 2-3 years that individual researchers have come up with projected costs for very, very narrow regions. But I would start high level. EPA CIRA is a great place to start. It kind of brings a lot of that together, and it has good references to go from there. But that would be my first stop.
Great. Thank you, Paul. Then there's a question here that relates to design philosophy. Shouldn't we start to change our design philosophy from one designing to a certain point in the future to one that is adaptable as change occurs? Jake, you talked about in the 4 levels there, level 3 or 4, thinking about risk and regret. How far do we go in design? And we want to minimize regret. So could you, Jake, and or Paul, talk about adaptable design? We don't want to just pick out a worst case somewhere far off in the future, design for that, and maybe we never get there, and it costs us a lot of money to build and design and build to a very significant goal. Could you talk about adaptable design a little bit?
Yeah, I think there are a few considerations, and one, it's what you're designing first and foremost, because it will be different by asset. But thinking about investment or an over adaptation or overspending, if we are looking at the worst case scenario and we are investing hundreds of thousands or millions of dollars in that adaptation, but when in reality that might not happen and we instead get a different climate, then are we overspending? And then underspending is the other side of that. If we take the lower end of these projections and we get a more intense climate, then how much are we losing? And I think that is a hard balance to maintain. And it does depend on some of these assets, because if you think about HVAC systems, although in 20 years, which is the lifespan of that HVAC system, the demand or the load on that system might be higher. If you oversize it by 40%, you will have losses in the first 10 years. And that is just one small example of all of the nuances of this sort of design. I think it does depend heavily on the assets. For roads, it's a little bit cleaner, and for some other systems, urban drainage, it might be cleaner. But even still, it's certainly a risk in investment, and thinking about over or underspending and regret, and looking across these models and scenarios and timeframes, because lifespan is also an important aspect of this, whether it's a 10 or 20-year lifespan, or for some assets that have 50+ years.
Thank you, Jake. Paul, anything to add to that?
I think that's perfectly. I would say that this will tie into, is there going to be changes in design codes, right, and standards? Our philosophy has to change, whether we're going to do it willingly or it's going to be imposed on us. And my feeling is you should start looking forward and anticipating this. So the standards aren't here yet, but there's enough, as you said, Dave, with the ASCE committee, there's enough professional associations looking at this. It's just a matter of time now before we're going to have changes. So the philosophy and the approach needs to start changing now, because it's going to be imposed very soon.
Yeah, thank you. And we have a couple questions here about standards and where they are in development, and what you two see and hear about and anticipate in terms of national and international standards from ANSI, ASTM, et cetera. And someone asked about the case study you gave, water utilities. Those are pretty large cities. What about small utilities don't have capacity to do these kind of studies? Can American Water Works Association or Water Environment Federation, can they help? Can they provide guidance? So there's standards and guidance. What do you two see evolving? Paul, you just mentioned you see people working on this, and what do you see evolving, and what kind of timelines? Will we have a lot more in 5 years, or what do you see?
Yeah, I'll take the standards part, and I'll let Jake take the what can be done. So standards are moving quickly. That we already have ISO climate standards that are being put in place. We see the at least the discussion, if not the preliminary inclusion of climate change into engineering standards in the US. I think the challenge that we're going to see is, how is that going to play out at a local level? My concern that I'll put out there is we could be in a situation where different parts of the country have very different standards and codes based on local politics. Unfortunately, climate change has become a very political issue. We can't avoid that. I hope that doesn't feed into the local standards, building standards, guides, codes. Then we'd have a problem. So this is where I think the national associations really have a primary role, is to push this information, push these guidelines so that it's not a bottom up. This is a case where we really almost need a top-down type leadership to make sure everyone's not just aware, but is doing something, because otherwise it could become very uneven and that could get dangerous.
Yeah,
And on accessibility for some of the smaller cities, towns, counties, I think it's a great point. And there are certainly funding opportunities and grants for those smaller places. I think that it's certainly going to become more and more common for federal funds and other funds to be diverted to it, which is an opportunity. And I think there's a lot of efforts going forth just from a national level, thinking about how climate change impacts these, whether it's water utilities or maintenance budgets or things like that. I think there'll be a lot of resources that small municipalities or cities can draw from as well. I think they're not far off from development, and I know it's certainly an internal task for us to try and get that sort of information out and in the hands of local decision makers. So
thanks, Jake. Thanks, Paul. That's great information for everybody. And former president of ASE, Dennis Truax, who is with us today, and Academy member, just put a note that ASCE 7, the big design guidance document with many subdivisions, 7 to 23, was updated to include climate change issues, and the next edition is continuing this process. And there was a lot of discussion about that at the ASC national meeting. And the American Academy of Environmental Engineers and Scientists is very much interested in this topic, hence our session today, and we'll be continuing to provide more resources like this for the membership and the broader engineering community. Okay, we have time for a couple more questions, and let's see. So there was a sea level rise. That was part of your presentation here, a highly visible, and as you nicely described, highly impactful aspect of changing climate. Could you talk about studies have been done on economic impacts to different regions, like Miami-Dade County, highly vulnerable, but they're not the only ones. Has there been pretty good study of what the potential impacts are? What can you say about that for the United States?
Yeah, so we have to kind of divide this into larger versus smaller sort of areas, or urban versus a little more rural or something. So a place like Miami's investing, hundreds of millions of dollars into raising roads, redoing their infrastructure, because realistically, that investment will pay off multiple times in terms of the economic impact. They're going to keep, Miami's going to be able to keep going. You're not going to move the city of Miami, right? For all the people who want to say we're going to have, everyone on the coast is going to move inland, I say, and we're not going to do that. Let's as engineers, we are going to come up with some solutions that we are going to technically blunt some of that impact. We may not be successful everywhere, but not everyone's going to get up. It also is an issue. Not everyone can pick up their life and move 1,000 miles inland, right? And this is where we really get to one of the things we did when we were looking at sea level rise was look at the cost to some of the smaller coastal communities. And here you really have situations where you have family farms that have been passed down 4 and 5 generations. People have lived in the same town for 70, 80, 100 years. Their whole livelihood is there. They're not on a whim just going to pick up and move. They're going to do everything possible to try and stay where they are. The challenge is there's one little town off of the South Carolina coast that's my favorite example, Pawleys Island, South Carolina. If anyone's ever been there, I finally found someone who had actually on one of these talks who came from there, and I was so excited about it. We found that the cost to each individual permanent resident there, if they were going to protect their island from sea level rise and storm surge, was going to be about $2 million a person. And they said probably people were not going to want that tax bill being mailed to them. But who's going to help them out? Somebody has to start making decisions about, are we going to use our technical expertise to try and save this? Is there economic and social value to saving these smaller coastal areas? I would say yes, there is, right? But if we look at it as purely economic in terms of, can these communities afford to do this on their own? No, they can't. Not everyone is a Seattle, a San Francisco, a Miami, or a New York that can put $500 million or $1 billion. Charleston is looking at $1 billion to protect their seaport. Well, it's one of the busiest seaports in the United States. There's huge economic impact there. But I don't think we want to get to the point where we're saying Charleston is more valuable than Pawleys Island. And this is where we get into an ethical discussion, a technical discussion. It's more than just economics. It is a social, it is an equity issue. And this is where engineers, and I say this a lot when we're talking to people who want to work with us and stuff, is climate change is going to puts engineers in a very uncomfortable position. It's not just you're coming up with the best technical solution. You are talking about people's lives. You're talking about the historic environmental justice issues. You're giving input on a lot of issues that we haven't really been trained historically to talk about, but climate starts bringing engineering into this, which also brings in the opportunity. It's bringing engineers to the table to discuss these issues way earlier than we ever did before. So it's a long answer to, there are economic impacts. It's why I believe that we are going to keep getting smarter, and we're going to figure out some issues. But there's also a big social component to this. And we can't forget that this doesn't just impact the big urban centers. There's a lot of areas in Louisiana and the bayous that people's lives are getting impacted, the Gulf Coast. So we have to start thinking this much more comprehensively.
Thank you, Paul. There were some questions here about ethics, the comments you made during the presentation, and you've addressed those head on here. Certainly there are big societal policy and ethical and social justice issues here, but there will also be, as you said, engineers on the front lines working with communities who will be asked to advise about issues with some deep ethics implications, and we all need to think about that.
It's interesting when you look back historically, some of the earliest questions in the United States government addressed was infrastructure, and should the federal government invest in canals and ports. And here we are over 200 years later, and we're almost back to that same question. What is the role of the federal government, of the states, in making sure our infrastructure remains world-class? And the more things change, they come back to where they were. And engineers are back in the forefront. We have to help make these decisions. It's a great opportunity.
Well, very well stated. And, I think that's why most environmental engineers get in this business, because of that complex interplay and of social, technical, scientific, policy, economic matters, and the ability to directly affect the lives of people. Paul and Jake, I think we'll have to stop the Q&A there. On behalf of everybody on the call, I thank you heartily for all the effort you put into preparing this, and for sponsoring the webinar today, and for helping to lead the charge on bringing climate change adaptation into environmental engineering practice. And with that, I will turn to Marissa for some final comments. Marissa?
Okay, thank you everyone for all your questions, and thank you, Paul and Jake, for sharing your knowledge with us today. If anyone would like to reach out directly to our speakers, please feel free to email them. We can put their email addresses in the chat here, or you can email me and I'm happy to share their contact information. We've enjoyed being with you all today, and we do have several webinars planned in the near future. So you can go to aaees.org/events to check them out and register. If you're interested in sponsoring an upcoming webinar, please reach out to me directly. Just a reminder, if you're not yet an AAEES member and you're considering joining the Academy, you can email me and we can discuss our membership options. And last but not least, our PDH certificates for this event will be sent out shortly. That's all for today. Thank you so much and have a great day, everyone.
Thanks,
Thank you all for joining us. Thanks again, Paul and Jake.
Bye-bye. Thank you.
Bye now.